All right. Good morning, everybody. Hope you had a good weekend. Right. So homolytic or homogenic, single-headed arrows for any of these radical processes. So let's look at that first. And I hopefully you had a chance to watch the videos that I sent over the weekend. I know that was a big game and all that stuff, but I think total is like 15 minutes. So let's look at that first example. Let me turn this off. Right, look at what we have over here compared to here. What happened?
Break the sigma bond.
I broke the bromine sigma bond. And based on the fact that each one of these got one electron here and here, right? Based on that fact, how did I break the sigma bond?
Homolytically.
Homolytically, right? So that means that when I break it, each atom that's in the bond gets one electron, right? So that's why those two bromines look like that. These are, again, radicals. It's an atom or a functional group. That contains a single unpaired electron. Right, single unpaired electron. Right, and the only way to do that is to homolytically break a bond, right? A sigma bond, because every bond is made up of two electrons. What about down here? If I wanted to bring these two together, how would I show it? How would I make the sigma bond between them?
You have two single-headed arrows going towards the inside.
Oh, wrong pen here. That's exactly right. Here and here, right? Always single-headed, never double-headed, right? Never double-headed when you're dealing with radicals. Right? Always single-headed, never double-headed. That's exactly right. What about here? Let's look at this. This is an example of what we call a radical addition. We know it's addition, right? Because we start out with a pi bond. Anytime you start with a pi bond as one of your starting materials, and it's the reactant, then it's going to be an addition. So how would you show this, right? Notice these are still the same two carbons. Actually, I'm gonna mark them. So this is a carbon here and here. And over here, same carbons. Like so, right? So how would you show that? It looks so sloppy, sorry. How would you show that happening? What happened? Is the pi bond still intact?
No.
No. What does it look like happening? It looks like I used the two electrons in the pi bond. I gave one of them to bromine, didn't I?
Yes.
To make a carbon bromine sigma bond. And then the other one just ended up here, right? So I can write this like this, right? I'll write this here, and then I'll write the bromine coming here, right? So these two coming towards each other means I'm making a bond on that carbon with bromine. Are y'all following that? Anybody not see that?
Can you repeat?
Go ahead.
So the unpaired electron from bromine goes on the hydrogen?
No. Let me fix that. That's a great question. And it looks like that, but it's actually going towards the carbon. You see the carbon in the bond, when that electron, that arrow is moving out away from the other carbon, that means that that carbon here is the carbon that's receiving the electron.
No, I meant the electron from bromine.
Yeah, so that
Oh.
electron is coming in to pair up with the electron that will be on that carbon, because I could draw it this way. Let me draw it out and then maybe it'll make more sense. Like if I have this is H. And then if I just show the bond cleaving, right, you'll see that there's an electron here and one here. Right, so if there's a bromine out here, when it comes here, this electron is coming here to meet it. So it has nothing to do with the hydrogen itself. It's the carbon that's reacting.
Okay, thank you.
Does that make sense?
Yes.
All right, all right. So this is an example of a radical addition. I'm taking bromine, I'm adding it to the pi bond. What about here? In the second example. What happened?
Are you just moving those the only electrons toward each other to create a bond?
Yeah, because you made a bond between these two carbons. Is that right? Right here, you made a bond between this carbon and this carbon, right?
Yes.
So all I need to do is show the electrons coming together. Right, that's the difference in homolytic and homogenic and heterogenic, is that if it's homogenic bond formation, both atoms that are reacting are bringing that one electron to the table. All right. What about the next example? What happened?
The hydrogen is making a bond with bromine, but it also breaks off from the carbon.
So I broke the CH bond, didn't I? You see that? And I also made a bond between H and Br. So the way I would show this is I would show the bond breaking here. One electron going back to carbon. Is that right? Is that accurate? Don't we have a single unpaired electron over here on carbon?
Yes.
Yeah. So, and anytime I want to show a step, like we'll talk about what type of reaction this is. But anytime I want to show a step like that, I always have to show that electron going back to carbon, and then I can just show the electron coming from bromine to here, right, to make a bond with that hydrogen. Right. This, we're going to see a lot of this in this radical chain reaction that we're getting ready to do. This is called abstraction. It's different from proton transfer. Proton transfer, you take off H plus. With abstraction, you remove a hydrogen radical. Right? Are y'all following that? So I have end up with HBr as a side product, and then I end up with a carbon radical. Right, this is a step. I'm gonna say it's a precursor to radical substitution. Which we're going to look at in a second. We got a nice example to work through. All right, so it's a precursor to radical substitution.
How did you say it was different from proton transfer?
Yeah, so with proton transfer that's the removal of H plus. Here we're removing H dot, like a hydrogen radical.
Okay.
All right, So now let's look at this last reaction right here. What happened? Looks like I made a carbon bromine bond. Is that right?
Yes.
Yeah.
From these two star materials. How would you show them coming together?
A single-headed era from the carbon and then one from the bromine.
Like that,
Yes.
right? Coming towards each other. That means I'm making each one of those atoms is sharing an electron with the other. And so we're making a single bond between them, right? This is an example of what we call a termination step. And this is usually the last step of a radical substitution.
I have a question.
Go ahead.
So I remember earlier, I think there was also like 3 steps for another type of reaction. This is totally different though, right?
No. You mean when we first started talking about this?
I think it was like initiation. and
Yep.
then,
It's the same. That was an introduction to this.
Okay.
Yeah, so it's not different. It's the same thing. So you have initiation and then propagation and termination. And propagation is where your extraction steps take place. And termination is where your combination reactions take place, where you combine your radicals together to get products. All right. So again, with these radical reactions, you're going to have, let me move this because that's not, I don't need that right here. With these radical reactions, what you have is, again, 3 steps. Every radical reaction is going to go through 3 steps. It's going to go through an initiation step. Well, not every radical reaction, but every radical chain reaction. There's some radical reactions that don't follow the chain reaction mechanism. Right, 3 steps: initiation, propagation, and termination. Right, so those 3 steps for every radical reaction that's going to follow is a chain reaction is going to follow this pattern, right? So here is asking us to do 2 things. It's asking us to calculate product distribution for monochlorinated products. All that means is that there's going to be 1 chlorine substituted on each product, product for the reaction of pentane with chlorine under radical chain reaction conditions. That's a lot of words. But what we're doing here is a radical substitution. Right, so radical substitution. What I'm substituting are hydrogens. I'm going to substitute a hydrogen for chlorine. All right, in these halogenation reactions. All right, so I have chlorine here. I use UV light as my energy source so I can cleave those bonds homolytically or have the energy present to do that. And in this particular molecule, since it's symmetrical, since I can draw a line here and basically cut it in half, can y'all see that? right? I'm only concerned with one half of this molecule. If you watch that Pac-Man video, this is the exact same molecule. I think it was pentane in there too. All right. So I'm going to get from here 3 different products. I'm going to get a product here where I have a chlorine here. I'm going to get a product here where I have chlorine here. And then I'll get a product here where I have chlorine on that end carbon. So 3 different products. All right. Those are my monochlorinated, meaning 1 chlorine. My monochlorinated products from radical substitution of pentane with chlorine. All right. Everybody following so far? We're going to show how each one of these is formed, by the way. And then at the end, we're going to go through how to calculate what we call the product distribution. Product distribution is basically just a ratio of products, and it's normally we only use that term when we're dealing with competitive processes, where you have multiple possibilities for product. So you got competing processes, then you have what's called a product distribution, because every product is not going to be formed in the same amount. All right. And with these, this is a primary radical, or this is a primary product, and these 2 are both secondary products. Right. So you more than likely you're going to get more of the secondary and less of the primary because of the stability of your radical. But we'll talk about that when we get to propagation. All right. So in the initiation, what's going to happen? Somebody who watched one of those 2 videos, what happens in initiation?
The chlorine, the 2 chlorines, they have like the valence electrons around them, and then they have single-headed arrow pointing towards the chlorines.
Like that?
Yes.
Right. So it's homolytic cleavage of chlorine. Is that right?
Yes.
All right. So this initiation step, this is my chlorine is my initiator. That's what's going to go into the chain or go into the next step, the propagation step, and do abstraction, right? Now in the propagation step or steps, no, right? I'm going to have I'm going to start here. Because remember, in propagation, what happens in propagation again? What's the process? Anybody? We just looked at it up top.
You have 3 different products. Is that what you're talking about?
Yeah, but what happens? You're right that you're going to get that you're going to get 3 different things. Yes, but what happens in propagation? What's the term that we just talked about up top? Let me.
Is it
The
product
monochlorinated
distribution?
products.
All right, let's go back up to here. Remember when we talked right here, what's happening in this step right here? I'm removing H dot, is that right? To get a carbon radical.
Yes.
And we said that the term for that process was abstraction. So in propagation, this is where abstraction happens. So abstraction is going to happen to form new radicals. All right. All right, so let's take the first example. All right, I'm going to abstract here. What color did I make that? Orange. I'm going to extract here. Abstract, not extract. We'll take this hydrogen off right here. How do I show that? With chlorine being the initiator and doing the abstraction. All right, what do the arrows look like for that process?
And go ahead, arrows pointing towards each other.
So let's keep this in mind. Whenever I'm doing abstraction, I'm removing H dot homolytically, right? So this is homolytic. Homolytic cleavage of the CH bond. Right, so I always have to show the electron going back to carbon, one leaving with hydrogen, and then one electron from the initiator. Right, same thing we just did up top. It never changes. I don't care where the hydrogen is. Those same three arrows are going to be present. You break the CH bond, and then you are using the chlorine to facilitate that process. So chlorine is pulling off H dot, right? So there's a bond being made between these two. That's why I get the HCl from on the other side. All right, so then what I'm left with is this radical. Let's make sure I got the right amount of carbons. I don't want to add any carbons. So that radical plus HCl. Is everybody okay with that?
Yes.
So that's what happens in propagation. If there's a chain present, the initiator that you make up top is just going to go in and start plucking off H dot, right, along that chain. And it's not going to do, I think I said this in that video, in the Pac-Man video, it's not going to do two hydrogens on the same chain, right? Every molecule is different, but it's happening very fast. Like this radical chain reactions are great reactions, but they're not always the first choice because they're not, sometimes they can be non-selective because the rate is so high that you get all kind of crazy products, right? And I'm gonna show you that with this example because we got time to walk this out. All right, what about the next example? So it's gonna be this plus a chlorine radical. Is anybody wondering how we're gonna have a third chlorine? When we only started with Cl2 up top.
Yes. Does it
Yes.
have anything to do with the light?
Well, not necessarily the light, but the stoichiometry, right? 1 mole of Cl2 molecules, right, is going to be 6.02 times, times 10 to the 23rd molecules. Hold up, I gotta shrink that. Per mole, right? So there's enough chlorine to, it'll never run out. Let's put it like that for the purpose of this reaction, right? Because for every 1 mole of Cl2, there's 6.02 times 10 to the 23rd molecules. So you got a bunch of these things floating around in solution. if that makes sense. It's not infinite, but it won't run out for the purposes of this reaction. All right. So let's go back to here. What color did I make that? Purple. So now we're taking this hydrogen with a chlorine radical. What's that going to look like? Is it going to be different? Somehow, is it somehow going to magically go through like a different process than the first hydrogen we took off?
No.
Nope. The only thing that's different is the location. All right, so I'm going to break that like that. Bring in the arrow from chlorine. This is where my HCl bond is going to come from. So there's no magic. Nothing changes, just the location. Right, and then that is here. That radical is going to be here. And that other hydrogen is still there, by the way, right? Because there are two hydrogens on that carbon, but only one of them gets subtracted. So that carbon still, that's why it's not charged, because it still has 4 valence electrons around it. All right, we're good with that one? Yes, no, kinda?
Yes.
All right. And then last one is here. What did I make that? Green. Ooh, wrong color. This is supposed to be green. Let me see if I can erase it without erasing everything. Right, and then now we're going to pull off this proton. I mean, sorry, this hydrogen. Any new anything new under the sun here? Is it going to all of a sudden become polar and use a double-headed arrow instead of a single-headed arrow?
No.
Nope, won't happen. Same process. Right, so now this is my HCl bond being formed here, and one of those electrons going back onto carbon. So I'm going to end up with this radical. That hydrogen is the other hydrogen that was there, still there, plus HCl. Any questions about the propagation steps? So again, in propagation, this is where you make your radicals, right? And it's a very simple process. Whatever the initiator is, that initiator is coming in and doing abstraction on some site on that chain. All right, because it's symmetrical, that means you're only going to get a certain number of products because the carbons on the left and the right are identical. So the two terminal carbons are identical. The two secondary carbons and then the central carbon, you know, is different from the rest of them. But you're not gonna have to show the mechanism for both ends of the chain. That's the point I'm making. Not to say that both sides are not equally susceptible to reaction, but for the purpose of what we're doing, we don't have to show it. All right. So you do in propagation, abstraction to form new radicals. And then in termination, that's where your products are formed. All right. So that's where your radicals from propagation, all three of them are going to come here. Actually, I'm just going to copy. if y'all don't mind. All right, so all three radicals here are now going to combine with a chlorine because that's the goal of the reaction. All right, we're following. Anybody not following? Say something. All right, so now it's just as simple as putting these together, right? And I think I already drew the products up here. I'm gonna cheat and copy. Don't cheat. All right, same thing on the second product here. You're gonna get the same mechanism, homogenic bond formation in each step. Like so. So those are my products. A common error when you're doing the termination steps is to make this HCl. There's no HCl involved in this step. Right, that's a common mistake that I see with these radical mechanisms is for the termination part, people will put in HCl as the terminating partner, and that's not true.
Okay,
All
so
right.
what happens to that H that was actually there in the propagation step?
You mean over here on these two secondary radicals? Like right here?
Yes.
It's
Yeah.
still there.
Okay.
Yeah, I kind of mentioned that up here. Like the H is still here. Let me write it in. The other H is still there. And that's what keeps that radical from having a charge, right? Because if you do the formal charge on it, it's got 4 valence electrons around it still. So you haven't lost that hydrogen. I just didn't draw it in, but I will.
No, I mean there's you have your radical up there plus HCl. What happens to the other part of the, I guess, products?
The HCl,
Yes.
good question. So a lot of times when you run a reaction like this, what you do is you aspirate it. So you put a needle, like you'll have a flask, like a round bottom flask. And then on that flask, you have what's called a septum. It's like a rubber stopper. And then you'll just stick a needle in. And then the HCl can come out as a gas. It can be expelled as a gas. So this is your reaction mixture. And every time you make HCl, you just expel it.
Okay, so it like disappears pretty much.
Mm-hmm. And it helps, right? It speeds the reaction up too, because if you follow in, like if it follows Le Chatelier's principle, the more HCl you get rid of on the other side, the more star material you're going to consume to keep up with the loss of HCl. So it's a win-win. Yep, and even the HCl that's not expelled, there's always a step in any organic reaction called a workup, which is at the end, where you might add in some ammonium chloride, or you may add in some other salt. And then if you, depending on what kind of solvent you're using, let's say you're doing this in like THF or dichloromethane or some solvent like that, you always have a workup step where you separate out your products from the trash or the side products that are in the reaction. So you'll take the reaction mixture, and in the workup, that's a good question. You'll have like what's called a separatory funnel. Looks kind of like this. Has a stopcock on the bottom. And then you put your layer, your reaction mixture in here. And let's say that's the organic layer. And then you'll have an aqueous layer. You shake them, right? So that the aqueous layer and the organic layer mix, you let it separate, and then you separate the layers out. So any side products you get that you don't want, if they're separable in the workup, then you'll get rid of them there. And then anything that didn't get separated, you'll get rid of it in a purification step. Normally, column chromatography, or if it's a solid recrystallization or something like that.
So it's almost similar to our lab in some way.
Say that again.
So is it similar to our lab in some way? And I guess.
Oh yeah, absolutely. The
Okay.
only thing we didn't do with the aspirin reaction is a workup. We didn't have well, we didn't have to because we got a solid, right?
Right.
So we didn't need to do a workup.
Okay.
Yeah, yeah. Great question. But every organic reaction is going to have some step at the end where you purify the product and get rid of all the side stuff. So anything that, like for this reaction, anything that doesn't get expelled, right? For this, these are all probably liquids, like 2-chloropentane, 3-chloropentane, and chloro. They're probably all liquids. So you'll take that more than likely and do a distillation. All right, so you'll distill off each one of those separate. But it just depends on the nature of your product. Whatever the type of product is going to determine what type of purification method you use. But that's a great question. Great question. All right, let me show you one other thing with this, and then we're going to actually not have a chance to do the percentages, but we can do that Wednesday. So remember I said how these chain reactions are great. They're really fast, but sometimes you get products that you don't want. So just like these chlorines can combine with your radicals, you also can have what's called a disproportionation. That's where your alkyl groups start combining. So more than likely you get some weird products, like sometimes, let's say this radical combined with another mole of itself like that. So you end up with a product like this. Right, that's an example of a disproportionation product. And that's what you don't want. If you're trying to get monochlorinated products, then you don't want your radicals that you made in propagation combining with each other. But a lot of times they do. And that's why radical chain reactions are not the reaction of choice. Like you don't pick this first, you try to find another method because there are a lot of different side reactions that you have to deal with, right? Or if you combined, let me shrink this so I can make room. Right, so let's say you combine this with this, where the radical is here, right? Then you end up with a product that looks like this, right? Which is not the product you're trying to make. No, hold up, I added an extra bond in there. Yeah, right? So that's bad, right? Because again, this is a side product that you don't want. And sometimes when you start getting those disproportionation products, it's very hard to separate, right? So yeah, that's just one of the drawbacks of using radical chain reactions. And sometimes you'll get like disproportionation reactions that where your radicals that you made in propagation start combining with one another. So yeah, we're not going to get a chance to get into the product distribution, right? But we do know I will say this, these are the secondary and versus the primary products are not going to be formed in the same amount. So this is secondary, that's secondary. But they're going to be formed in unequal amounts. All right, so we're going to actually stop right here instead of trying to push through and finish that the product distribution part. I'm going to stop right here. And then we'll pick this up on Wednesday. Said the recording stopped. Did it really? It looks like it's still recording.
It's still recording.
Yeah. All right. I think that was early. Yeah, that was at 10:06. Yep. Thank you. I think it's Chelsea. Hope I pronounced that right.
It's Sanaya.
No. I'm talking about somebody who messaged me and told me it stopped.
No.
Yeah, but go ahead. Any questions? Let me stop recording now though.